Welcome back to Probability and Statistics 1. We're continuing our discussion of color sequences with replacement. Up to now, we've defined and studied a couple of different random variables associated with this process. We discussed the indicator variables, I sub k, that represent whether trial number k was a success, that is a red ball, or a failure, a green ball. And we've also discussed the binomial random variables n sub n, which represent the number of successes that occur in trials 1 through n. Today we'd like to look at another family of random variables associated with the process, and these are variables we'll denote by t sub j. And what t sub j represents is the trial number of the jth success. So for instance, t sub 5 would be the trial number on which we drew the 5th red ball. And so we'd like to understand these random variables in the same way that we have the previous ones. Well, particularly in this case, we're going to focus on the probability mass function for the t sub j's. So again, let's think about this variable sort of from a mathematical point of view. T sub j is the trial number of the jth red ball. And like all the other variables we've seen, the t sub j's can actually be expressed, can be reduced to statements about the I sub k's, right? I mean, that makes sense because the variables I sub k, that sequence of values, contains everything there is to know about the color sequence. So t sub 1, which represents the trial number of the first red ball, the first success, you could express as simply the minimum index such that I sub k is equal to 1, right? So if your color sequence was, for instance, 0, 0, 1, then the first red ball would have appeared on trial number 3, and so t sub 1 would equal 3. T sub 2 similarly can be expressed in terms of the I sub k's. T sub 2 would be the first index k that's greater than t1, right? So it comes after the first success, but it's the first index after the first success that is a success. So that would mean it's the second success. So it would be the first index k such that k is bigger than t1 and I sub k equals 1. And that would be t2, the time of the trial number of the second red ball, and so on. So these variables t sub j are known as negative binomial random variables with parameters j and p. So let's think about the probability mass function of the variable t sub j. So we want to know what is the probability that t sub j equals some specific integer n, let's say. So for instance, what's the probability that t sub 5 equals 20? In other words, the probability that the 5th red ball occurs on trial 20. Well, to do that, as usual, we'd want to look at that event, that t sub j equals n, in detail. So think about the event that t sub 5 equals 20, for instance. What color sequences does that correspond to? Well, if t5 equals 20, that would mean that the 5th success occurs on trial 20. So you definitely would have a 1 in position 20 of that color sequence. What about positions 1 through 19, right? Well, draw number 20 was your 5th success. So that means the 4 remaining successes have to be somewhere in slots 1 through 19, right? So the remaining slots would have 4 ones in them, and the rest would be zeros. So in general, if t sub j is equal to n, what you have are color sequences of length n, whose last entries are 1, and have the property that in the remaining n minus 1 entries, there are exactly j minus 1 ones and n minus j zeros. So by the theorem 3.8 on color sequences, each one of those color sequences would have a probability of p to the j times 1 minus p raised to the n minus j. And why is that? Because each one of those color sequences has exactly j1s, right? Because there's been j successes, and n minus j zeros. The only question then is, how many such sequences are there? Because our event that T sub j equals n is the disjoint union of all those color sequences. All those color sequences have that same probability, pj times 1 minus p to the n minus j. So I just need the number of those color sequences. And that's simply going to be n minus 1, choose j minus 1, right? Because in those n minus 1 blanks to the left of the 1 there, you've got to pick j minus 1 for the remaining successes. And so there's n minus 1, choose j minus 1 ways of doing that. And that tells us that the probability mass function for T sub j is given here. N minus 1, choose j minus 1, times p to the j times 1 minus p to the n minus j. And this is good for n greater than or equal to j. That little restriction just makes sense, right? If you're looking for the trial number of the jth success, that has to be, the trial number has to be at least j, right? You couldn't have 5 successes in the first 3 trials. You have to have at least 5 trials in order to have 5 successes. So that's why n has to be at least as big as j here. And this thing is known as the negative binomial distribution with parameters j and p. And so a special case of this is when j equals 1, and there we're looking for the trial number of the first success. This is similar to kind of problems we've done previously, like, you know, what's the probability that if you roll a 6-sided die, the first 3 appears on trial 5? That would be T1, right? For the probability that T1 equals 5 there. And when j equals 1, the distribution has a special name. It's called the geometric distribution. Here's some pictures of the negative binomial distribution. The one you're looking at here is for j equal 2 and p equal 1/2. So the probability of a success is 1/2, and this is the distribution of the trial number of the second success. Here's the distribution of the trial number of the fourth success when p is 1/2. And here's the distribution of the trial number of the 8th success when p is 1/2. So these negative binomial distributions are a little bit more varied in their shapes than the ones we've seen before, the binomial distribution and the Bernoulli distribution. We'll continue our discussion of the color sequence process in the next video. What we're going to look at next is a property. We're going to go back to the indicator variables, and we're going to look for a certain property that they have that's going to turn out to be sort of the defining property of processes like this. It's a property known as independence, and it plays a fundamental role in all of probability theory. So we'll open that book when we do our next video. In the meantime, take care. Let me know if you have questions, and we'll be back at you real soon.